So continuing on with the idea of subsets, we need to talk about the idea of a proper subset. And here's the definition. If X is a subset of another set Y, but X doesn't actually equal Y, then X is called a proper subset of the bigger set Y. And here's the notation. It's the same kind of sideways U shape, but we've lost the line underneath. And the way to remember that relationship, or what the difference is between a proper subset like this one and then just the regular old subset, is to think about the two symbols for less than or equal to and the less than symbol. Did someone say something? Or was that just an inadvertent sound? So with this one, the less than or equal to symbol, there's a possibility that the thing on the left could be equal to the thing on the right. So just picking an example, if X is less than or equal to 3, then it's possible for X to actually be equal to 3. But if I use the strictly less than symbol like this, X is less than 3, then in this case, X can't be 3. It has to be, like 2 or 2.9, something like that, something smaller than 3. And the same sort of relationship holds between sets, subsets, and proper subsets. So in a proper subset like this, X can't be quite as big as Y. It can't have as many elements as Y. If you have the line underneath, then there's a possibility that this could be the whole set over there. Let's see. Okay, so to pick a small example for this, we can have a little set with maybe 2 letters in it, A and C, and this is a proper subset of this one, with the first 3 letters of the alphabet in it. So all of these letters are in this set, but this set has an extra letter as B, and B is not over here. So that's what makes it a proper subset. Any questions before I move on to the next page? Oh, there was a question in the chat. So Shelby's question is, so does that mean an empty subset is a proper subset of any other set besides another empty set? And yes, you're completely correct. So let's see, a little more room. So the empty set is a proper subset of anything that you can think of except for the empty set itself. So remember, this is just a symbol for the empty set, and these two are actually equal to each other. They have the same elements because, well, they have no elements. And there was another question, would the set BA be proper? And the answer is yes. So with sets, the order that you put things in doesn't matter. This is exactly the same as this set. Usually when you're writing things like this down, you would probably put it in alphabetical order just because it's a good way to organize things, but it doesn't actually matter. They're still the same. So next up is the idea of a power set. The set of all subsets of a set, so this is a mouthful, the set of all subsets of a set X is called the power set of X. And it has this special notation, capital P with X in parentheses. So this is something like a function. So I'm sure you've seen functions like f of x or something like that. And I need to work on my spelling. You should think of this as something like a function. So the input is your set. And the output of the function is all of the subsets. So let's take a small set, maybe one with three letters in it, like we were talking about. And then now let us think through what the power set of this one looks like. So what are all the subsets of X? So someone just start telling me what some subsets could be of ABC.
A, B.
A and B? Okay. So just keep going.
The empty set.
Empty set, good. So I said a second ago, the empty set is a subset of everything. And let's see, I see another one in the chat. A and C together. Can you say that again?
C.
Just C by itself. Good. Okay. So we're about halfway there. Can you think of any more?
Just A and just B.
Good. So just all the single elements by themselves.
BC.
B and C. Good. And there's one more.
ABC.
The whole thing together. Good. Right, and that's all of them. So the next thing I want to do is point out the relationship between the number of subsets and then the number of original elements. So how many subsets did X have?
8.
There's 8 of them. And we have 3 elements here. Can you think of any relationship between 3 and 8? This one's kind of hard to guess. So 8 is actually 2 to the 3rd power. So 2 times 2 times 2. Okay. And if you have any set at all, any finite set with just some number of elements, then the number of elements in its power set is 2 to the number of elements power. So I can write this down using our mathematical symbols that we've learned. If X is a set, if the number of elements in X is equal to the number n, then the number of elements in the power set is equal to 2 to the n. So here's a question. If I started with a set with 10 elements, how many subsets would it have?
2 to the 10th power.
Mm-hmm. So how many is that, just to get an idea? Right, 1,024. So if you have 10 elements in your set, if you wanted to write out all of the subsets, there would be over 1,000 of them. And the reason is this exponent. Exponential growth is sort of it's in the English language to mean, something that blows up really fast, like this. So if you have 10 elements, it's already over 1,000. If you have 100 elements, or not even, yeah, let's say 100. If you had 100 elements in your set, which is still not that many, you would have over 1 million subsets. So you probably don't ever want to write out the power set for anything unless it's very small, like this one that only has 3 elements. Okay, so now we're going to move on to set operations. So these are going to play the role of things like addition and multiplication when we're dealing with numbers. They're ways to combine sets, like we can add numbers to combine them. Okay. So here is the basic definition for a union. If we have two sets, X and Y, then the union of the two sets is represented by this symbol. So you put a U symbol in between the two sets. And if we use set builder notation, it would look something like this. The union of X and Y is the set of X, little x, such that X is either an element of Y or X. So a union combines the elements of X and Y. So you might want to think of this as something like addition. An intersection is kind of the opposite of a union. So here we're looking for things that are in both X and Y. And the symbol also gets flipped upside down. So its symbol is also the opposite of a union. And the way to think about an intersection, it says all of the elements in both sets. Okay, and then our third operation is a difference. And this is written exactly like subtraction. So we sometimes call subtracting two numbers finding the difference. If you want to find the difference of two sets, what you do is you find the elements in this set that are not in this set. So it's like you're subtracting all of the elements of Y from the set X. And let's look at a little example with some small sets for some practice. My first set X is going to have the first three even numbers, 2, 4, and 6. And Y is going to be the first 4 positive integers, 1, 2, 3, and 4. And what I want to do with these is just look at the union, the intersection, and then we'll take the difference. Okay, so what is X union Y? Let's just list out the sets, elements. So you said 2 and 4 in the chat. That's actually the intersection. So 2 and 4 are in both sets. What would the union be?
1, 2, 3, 4, 6.
Good. So we just put all of the elements together. 1, 2, 3, 4, and then 5 isn't in either of them, but we do have 6. So all of the elements together. And you should pay attention that I didn't have to write 2 and 4 twice down here. So once you have a set or an element in your set, you don't have to write it more than once. What about X intersect Y? I guess we already know that one. We're looking for the elements in both. So 2 is there and there. And then 4 is there and there. And there aren't any other elements that they share. Good. Okay, so what about X minus Y, the difference? So which elements are in this set, but not in Y?
6.
6, good. So 2 and 4 are both over here, but 6 is not. So 2 and 4 get taken away, and 6 is left over. What about Y minus X, if we switch around the order? So what elements are here, but not over there?
1 and 3.
Good. So we keep the 2 odd numbers. 1 and 3. Okay, any questions so far?
Can you minus an empty set from itself?
So you're asking what, and
Yeah, is there a difference between an empty set and an empty set?
what do you think the answer is?
I don't think there is an answer.
You think it just doesn't have an answer?
Yeah.
Okay. It actually does. So what we're looking for is to take away any elements that are in this set from that set. But since there aren't any elements in the empty set, we can't take anything away. So you still just have nothing left. So it's still just empty. You started with nothing, you're taking nothing away, and you still have nothing. And I guess this is something that I'm going to write down in a few minutes. But if I start with any set and I subtract off the empty set, I'm not taking away any elements. So nothing happens. I still have what I started with. And the way to think about this is just like subtracting 0, the number. It works exactly the same way, the empty set and 0. Right, so just like 0 minus 0 is still 0, that's exactly why this works the way it does. Okay, so in this next example, let's talk about maybe a few of the common mathematical sets. Like what would happen if I took the integers and with the union of the real numbers? What do you think?
Aren't they already the same?
So you mean all of the integers are already over there in the real
Yeah.
numbers? Yes, exactly. So we're combining elements from the integers that are already in the real numbers. So we're not actually adding anything new. And someone said this in the chat, yeah. It is just the real numbers. What about the real numbers and then take away the rational numbers?
Would you get 0? Or
Uh,
not 0, but an empty set?
no. So what you need to think about are things like the number pi and like the square root of 2, and those would still be left over. And someone just said in the chat that this would be the set of irrational numbers, and that's exactly right. So if we take away all the fractions, all the quotients from the real numbers, we're left with the irrational numbers. Like pi and the square root of 2, and those sorts of things. Good. Any questions before we move on to the next page? Okay, so moving along. So I mentioned on Wednesday that our sets can have sets inside of them, and there's a special name for a set that only has sets inside of it. And this is it. A set whose elements are themselves sets is called a family of sets. So it's something like a collection of sets. And you can think of anything as an example, like this one. So this is a set, and all of the things inside of it are sets. So this is called a family. And I want to get down to here talking about pairwise disjoint families. But before we do that, I have to tell you actually what disjoint even means. And what it means is if two sets are disjoint, then they don't have any elements in common. So that means their intersection is empty, equal to the empty set. So for example, the set with A and B intersected with the set containing the next few letters, maybe C, D, E, F, is equal to the empty set because they don't share any letters in common. And that means they're disjoint. Okay, so something that's a little bit more important are what are called pairwise disjoint families. So that's where you have a family of sets, like this one up here. But if you look at any two sets in your family, they're going to be disjoint. Their intersection is empty. So what's a good example? Maybe just using some numbers. So this is a family of sets with the first 9 integers, positive integers. But each of the sets in my family are disjoint from all of the other ones. So if I compare like the first set with 1 and 2 to the second set, they don't have anything in common. If I compare it to this one over here, 1, 2 compared to 4, 5, 6, nothing in common, nothing in common there, and then nothing in common with the last set with just 9 in it. So compare this to the next set. So this one is pairwise disjoint. So there was a question if you should compare any set. Yes. So you should also think about what happens if you compared the second set with any of the others, or the third with all the others, and so on. Aren't empty sets? Okay. So how to answer that question. So the empty set doesn't have anything inside of it. So if I took the empty set and I tried to see what it had in common with any other set, let's say 1, 1 and 2, what's in common between these two sets? What elements do they share? Well, there's nothing in common because there's nothing in here that could possibly be in common with this set. So this is just the empty set. So if you look at the intersection of the empty set with anything else, like I did here, it's always going to be empty. So that means the empty set is disjoint from everything, actually. So compare this pairwise disjoints family to this next one. the first two sets don't share any elements in common, and the first set doesn't share any elements with the third set. But if you compare this set to that one, they do share two elements, C and D. That means this one is not pairwise disjoint. Yes, and my notes got a little bit out of order, so I'm going to okay, we'll come back to that later. Never mind. Just continuing on. So sometimes we're only going to be dealing with subsets of a certain bigger set, and I'm going to call it U. And the reason I'm calling U is that we call this big set a universal set. So U for universe. So before I continue on talking about the next part of that paragraph, let me give a good example. So in algebra, so think back maybe to your first algebra class, the real numbers form our universe. Let's say algebra 1. So maybe you don't know anything about complex numbers yet. So thinking back to like your high school classes, everything that you dealt with probably were real numbers, and the set of real numbers formed your universal set, because everything that you dealt with lived inside of the set of real numbers. Okay, so well, what are some examples? Like the integers, the rationals, even going to geometry. Maybe you have a circle with radius 2, so you look at something like 4 pi if you wanted to find its area. And maybe your set has some other weird numbers in it, like e, or 4 pi minus 5e. Right, these are all real numbers, and they're subsets of R, the reals. So the next thing I need to talk about here is this idea of a complement. So if you're thinking about this sort of situation where you have a universal set, like the real numbers, and you have some subset of your bigger set, then there's a special name for your universal set minus your smaller set, and it's called a complement. So for example, if I have the real numbers as my universe, and I'm looking at the set of rational numbers, and I want to find its complement, so we draw a little bar over our set for complement, then this is the real numbers minus the rational numbers. And these were the irrationals. Okay, any questions before we move on? I'm hoping the next picture will help to clear things up. So next, I want to talk about the idea of a Venn diagram. This is probably something that you've seen, maybe even going back to elementary school when you're comparing groups of things. Let me just draw a Venn diagram here for us to look at. So I draw a box, a large box, and I think of this as my universe. This is my universal set. And my other two sets that we're going to consider live inside of it. Maybe I'll label this one X and this one Y. So I have a universe represented by this box, and then I have two sets living inside of the universe, X and Y. And you can see that I've divided the box into several different regions, and let's just label them 1, 2, 3, and 4. And then try to relate those back to the symbols that we've been talking about. So what is 1? First of all, looking at the picture, we can see that it's the elements that are in the universe, but they're not inside of either of these two sets. And if we wanted to put that in mathematical symbols, that would be starting with U, and then I need to take away both of these sets. I need to take away X and Y. So I'm taking away the union of the two. And this is what we called the complement. So we have our universe minus a set. So that's a complement. Let's move on to 2. So this region here, all of this region is part of X, but it excludes anything over here that was in Y. So this is the elements of X with any shared elements with Y taken away, or X minus Y. The third region is where X and Y overlap. So that's the intersection of X and Y. And then the fourth region is the set, or the region contained within Y, but not X. So that's going to be Y minus the elements of X. Okay, so when you're thinking about sets and you're doing things like intersections and unions and subtracting, sometimes it's helpful to make a picture like this Venn diagram to try to clear things up in your mind, because usually thinking something through visually is a little bit easier than trying to think through using these symbols until you get lots of practice using the symbols. And it looks like that's our stopping point for today. Does anyone have any questions here at the end of class? homework. So since I didn't finish the section today, it'll be due next Friday, and I'll go ahead and adjust that. But you should get started. You can do most of the homework now. You've seen almost everything, so please get started on it. Thank you. Yeah, it's just a little fountain pen. Here's what it is if you want to go get one. Okay, so if there aren't any other questions, I will see you guys on Monday. If anything comes up over the weekends, please feel free to send me an email, and I'll get back to you.